So moving up here in our interesting and neato applications to all these things, magnetic force on a current carrying conductor. So with electric stuff, we started with electric fields, electrostatic force, all that stuff, potential, and then we built up to circuits, which is a supremely useful thing. And so we're going to do a similar thing here where we now jump up into supremely useful things because of this magnetic force. So I'm going to describe a couple things in the remainder of this lecture that utilize this, but it starts with considering, instead of the magnetic force on a moving single point charge, the magnetic force on a current, like charges traveling along a length of wire that is in the presence of a magnetic field. So I'm not going to derive it, I'm just going to write it down, and it won't look so mysterious. So I is current, right? And L is going to be the length of wire, and we're going to say that is the vector here, not the current, cross B, because current is a scalar, not a vector. But a length of wire can be a vector, a length of wire that's, pointing or traveling in some direction, right? So that can be a vector, and that'll be vector L here, has some length L, but it's also pointing in some direction, so that would be different than some length of wire here pointing in some other direction. It's still the same length, L, but the L vector is pointing in a completely different direction, right? Compare this guy to this guy, it's different direction. And that matters because if we have a magnetic field that is, say, like this, if we reorient our wire, it might experience a magnetic force, according to this right-hand rule, right, in one orientation, but not another. Invariably, it will be different depending on which orientation, right? So you move it just a little bit, it'll matter. Okay, so in this case, of course, I is current, L is the length of wire, and B is the magnetic field strength. And the direction of the force, same thing, determined by the right-hand rule. So I think I describe the right-hand rule here in the notes, but what I want to jump to is a common device that operates using the magnetic force on a current-carrying wire. And it's something that is surprisingly accessible to us, and it's the speaker. So if we have, let me get a whole new space here, and let me think about what colors I want to use. Well, if we have some speaker cone like this, right? And we have a voice coil. So I'm going to use, what should I use? Blue for the current, I think is what I had used. So we have the current that is traveling around in this way. So I is not a vector. We have the current going around like this because it is wrapped around something, right? You have wire that's wrapped around some cylinder like this, and the wires, wrapped around it like this, right? So you have current going around in this way. Oops. I'll do this. And you have a magnetic field, which is the north part is this center piece that the wire is wrapped around. So this is north. And the south is out here. And I'm going to draw it on this side too. And we're seeing kind of like a cutout version of this. So this is south, south, right? North and south. that means you would have magnetic field lines in this cutout kind of version from north to south. This is the magnetic field lines, and then over here go from north to south. And I'm not drawing them as loops, but they exist as loops, right? So they exist as loops, kind of, you know, to give you an idea, kind of like this, right? But I'm not going to overcomplicate the drawing. They exist as loops, but in that area that we care about where there's current, in other words, like right here, this is where all the magic happens, right here, I'm going to blow out this scenario over here. So to produce the current, one last thing I'll say, to produce the current, there's some, you know, connects over to some potential difference, right? And so there's current, and it goes around the coil a certain way, right? And it's wound up, and then it comes back along this way, right? And the charges are then stepped up in potential. We talked about all this stuff. They're stepped back up, and then they go and complete their journey. So that's the electric side of the circuit that needs to be attached to this. So we have basically just wire with current running through it, nothing else fancy, caused by some battery or potential difference or something. And the current is going around and around and around the north end of a magnet, and the south ends of a magnet are in the outside of this thing, to produce a B field that is radially outward from that north part of the magnet, up in this region and down in this region. And so let's look at the situation right here. And obviously the convert is, you know, similar thing is happening below. So let's just look at that. So in that situation, we have current going into the page, right? And we have a magnetic field that is towards the top of the page, from north to south of the magnet. And so the resulting force, I'll use purple. The resulting, I'll use this. Resulting force, if you put your pointer finger into the page, your middle finger then goes to the top of the page, your thumb of your right hand, if you're holding your fingers in that kind of axis orthogonal position, your thumb should be pointing to the right. And so this is the magnetic force on the current in that wire. So therefore, this whole entire block here experiences a force to the right, right? Because the wire is what has experienced the force, but the wire is attached to that north end of the magnet. And so that whole thing as a unit kind of experiences this force, F equals ma, right? With this thing having some mass, this whole north end of the magnet and the wire wrapped around it in a coil, that has some mass, and it experiences some acceleration to the right. So it moves to the right a little bit. And if the current were reversed, so a moment later, if the current were reversed in the reverse direction, you can think of it as instead of the potential difference being like this, we then switched it, so the potential difference is like that. So now the current is going this way, right? Oops, not a vector. And then I won't messy up the drawing, but the current then coils around the opposite direction. Let's look at that situation. So now the current is pointing in the opposite direction. So now the current is out of the page at the top part here, right? Looking here, but flip the direction that the blue is going, right? It's going like this. So it's coming up out of the page, but the magnetic field is the same direction. So that's still from the bottom of the page to the top, so pointing straight up. So what's the resulting force, F, on this? We have to use our right hand. Put your right hand in the direction of current. So this circle with a dot is a 3D vector that tells us up out of the page. The magnetic field is pointing still to the top of the page, and so your right thumb should be pointing to the left. So now the force here is to the left. And so in this moment too, when we've, post flipping the current, then you have some force F this way equal to MA. So that whole block, that whole north end of the magnet with the wire wrapped around it experiences some force and acceleration to the left, right? And so if it's allowed to kind of move just a little bit in place, and if we have some way to send current in some, very easily flippable way, one direction or the other, then we can move and vibrate this thing at our will according to the direction of current. So in other words, if we can oscillate the current, the direction of current that is running through those wires at whatever frequency, this thing will be vibrating left and right. And be vibrating left and right, and thus pushing air molecules out here in the speaker cone, right? All these air molecules out here will become, compressed, right? Compressed, and that will then propagate out, and you'll have a compressed version as the block moves to the right of air that then moves out and eventually, reaches your ear, and you hear a certain frequency of density fluctuations of the air, which is sound. So it all comes down to the motion, the controlled vibration through time of this magnetic north block with wire wrapped around it. And it's really only one force that's causing that, and that's the magnetic force. And it's caused by this, QV, or here in this case, I L cross B. Current in a wire of length L oriented in a certain direction in a B field, which is produced by a north-south magnet orientation to produce the magnetic force on that current, which moves that whole block. I just think that's so cool. So that's how a speaker works. So given a battery, like any battery that you can find in your junk drawer, and given a magnet, a north and a south magnet, you can get these horseshoe magnets or neodymium magnets if you want to go super strong, and given just like a piece of metal that's arranged in a nice long segment, you can now create a speaker, a really rudimentary speaker. I bet you did not think that you'd be able to engineer that by the end of this lecture. And you'll find something else that's even cooler later.